On electromagnetism. It's in the magnetism unit, and the first question here is something you should have before. What kind of field is produced by a moving charge? And the answer is going to be a magnetic field is produced by that moving charge. So just a reminder, we could have a charge that's not moving, and we call that a static charge. And that's going to produce this thing called an electric field. Or we can have a moving charge like you see here, and this is what creates that magnetic field. And you can tell it's a magnetic field because it's going to interact with a compass. So if I took a compass like this, it's going to face a certain direction based on the direction current is moving, and you're going to learn a little bit about that today. So this one up here would not interact with a compass because a compass just is nothing more than a magnet itself. So you need two magnets or a ferromagnetic material and a compass to interact together. Some of the variables you're going to see here. Magnetic field is a new thing that you didn't have before. We're going to have the variable B that we'll see in our equations. And that is the unit, which most people know this as a car nowadays, or a person is a Tesla. And the unit, so after the number, like if you have 6 something, it's going to be 6 Teslas, capital T. Current, you've seen this before, it's going to be the variable I. It's ampere as a unit, and then A is what you put after a number. Then potential difference or voltage, once again, same thing, different ways of calling the same thing. You can use the variable V, and it's going to have the unit, the volt, which will also have a unit, the same as the variable, which will be also capital V. So what is a right-hand rule, and why would you use it in physics? So what I want you to do is whenever possible, if I'm getting too quick, you just have to pause the video and take any notes that you might have. And then you can kind of get back to answering questions and different things. But you're in charge of not falling behind, so make sure you pause the video because I might talk quick at times. And when you pause the video, you can kind of catch up, and then you can hit play, you can hit rewind, do everything you need to answer these kind of questions. So this one you haven't really had yet before, but what is a right-hand rule and why would we use it in physics? It's nothing more than this, and this, if you have my set of notes, you can just write this down. It's a mnemonic, something we use to remember something. Just remember a concept. It has nothing to do with electricity, with current, or magnetism at all. It just happens to be that we're going to use our right-hand rule, and at times we're going to use our left hands to notate a few things. But all it is, this right here, that's what you have to write down, are right-hand rules and mnemonic used to memorize a concept. And we're going to have a couple, and these different right-hand rules are going to have nothing to do with each other. So one at a time, your finger might be the magnetic field or a current, and the next time your thumb's going to be it. So you just have to kind of go with each rule individually. Some things we're going to use are direction signs. So let's just remind you of a few things. We have up or north, up, that way. To the right, we have right or east. Down, we have down or south. To the left, we have left or west. Now, just a note, if we're using west, north, east, you want to answer the question with south. If we're using the direction signs, use the same direction lingo that you would have before. So if we use up, left, right, down, you want to kind of use the same lingo back. Now another thing you're going to see is, because now we're going to have to go a little bit three-dimensional. We can't just go to two-dimensional like this. And so we're going to have the symbol that is towards you and the symbol that's away from you. And what this comes from is an arrow being shot at you. When arrow's coming towards you, you're going to see the tip of the arrow towards you. And if the arrow was going away from you, you would see the crosshairs at the back of the arrow. So current through a straight line, just a reminder, if we had a battery, we have our positive terminal of the battery, we have a negative terminal of the battery, or if we drew it in a previous lesson, we had this going on right here. And current's always going to flow from positive to the negative. Current's going to flow through the positive to the negative. So if you ever see that notation right here, current, either seeing this, that current's flowing that way, or you might just see that symbol I, or the variable I and an arrow telling you current's flowing that way. But either way, you don't need both. One of these, the top or the bottom, that little notation plus a negative, or just an I and an arrow would tell me the direction current was flowing. And we are following the conventional current. So even though electrons, protons don't flow, we're still going to pretend like it's a positive flow from positive to negative. And just something that's a bunch of engineers and physicists, some more engineers came up with. Benjamin Franklin started it. Current through a straight line wire. So this is our first right-hand rule. And so this can get difficult for students. So you just have to kind of realize your right hand has nothing to do with much of anything, but you have to hold your hand up and hold your hand in a thumbs up position, just like this. And what I would do is place your thumb in direction of current, which you'll see in a second. Is I would probably take a pencil and put it in your hand, and so the thumb is in the direction of the pencil. So wherever the tip, take the tip of the pencil and face in the same direction as the thumb. If current in a wire was going in the direction from the back of your pencil to the top of your pencil, and so if I was holding a pencil like right here, the tip would be over here, and that would be inside. There's your eraser. Um, the current in the direction of that pencil, well, the curl of your finger is going to tell you the direction that the magnetic field is going to be. And so we'll look at this a little closer. It's going to follow the direction. And so it's going to tell you, if I had a compass and I put it on top of a wire that was held in my hand, it would tell me that the north was down. It would have, the wire would give off a stronger magnetic field than the world around us, so it's going to interfere. It's going to interact with the compass a little bit more. So here's a picture of if you go ahead and hold your thumbs up and then take your hand and face it towards your face and look at the curl of your hand. So you should see what you see right here. So your pencil will be facing towards you, and you should see this curl of your hand. Well, if current is traveling towards you, no matter where I had a compass pointing, take a look at this animation right here. Well, as soon as current's flowing, the arrows or the norths of these compasses are going to face in a certain direction that will follow that curl of your hand. And that would go all the way around your hand. So it would just keep on going around that direction. That's all this is telling you. And it's determined by this right hand rule. Once again, the curl of your hand. Wherever your hand is, if you were looking at this part of a wire, that the current would be the north of a compass would be facing that direction. Looking at this, the north of the compass would be facing this direction. Once again, I'm taking this and making it relate to compasses by doing that little animation up top. Okay, so if current was flowing away from you, so this one's a little harder. You're going to have to put your hand kind of facing away from you, just like this picture. Now your pencil, you should be looking at your pencil eraser if you're holding a pencil like this. Well, now you just switch the curl of your hand, and therefore you're going to switch the direction that north is facing. So this is the same right hand rules before. It's just now we're going to go ahead and we're going to have current going away. And that little X is representing current going away. And then current anywhere around this arrow. If I put a compass right here, it would tell me that north is to the left if it was below that wire with current flowing away from it. And that's because of the magnetic field that's created. So this is the blank pole of a compass will point in the direction of the magnetic field, and that is going to be the north pole of a compass. So right now, if I held a compass around a wire, it's telling me the magnetic field on this side, so the wire is behind the compass, it's telling me the magnetic field on this side above this wire when looking at it into the screen is upwards. And then I can use that to determine some other things like the direction of the current of the wire. This would tell me enough. So current towards you creates a magnetic field that makes the compass do this. And depending on where you look around that wire now, so this is current coming towards you. So just hold your wire, look at the tip of your pencil facing towards you, and look at the curl of your hands. It's going all the way around just like that. Now you can go ahead and do the opposite. Go ahead and turn your hands so your hand's facing the opposite direction, and all of a sudden now your curl of your hand is facing the other way. I'm kind of going backwards, but same principle. But now the curl of your hand is facing away, so anywhere you put a compass around this wire would tell you that the direction that you see in the red of these compasses are the direction of north. Current in a straight wire down, so if current's going in this direction, downwards. When there's no current, there's no interaction. It's interacting with the Earth, and according to this, the Earth was north, it was up. The south magnetic pole, which tracks the north pole of a compass, was up. But once you run current downwards, you can kind of take your thumb, your hand, face it downwards, just like you see the picture I have down there, and in front of the wire, the compass would be telling you this way is north, and behind the wire, the compass would be telling you that way is north. But really, if you had the compass on the side, it would be telling you something different. It would be telling you inwards is north, and if you had a compass over here, it would be telling you towards you is north, because it's really a circle all the way around that wire. And so that's all this is saying here. You follow the same orientation, just everything's been the same. It just depends on how you're holding your thumb. It all depends on which way is current. Is current going to the right? Is current going left? Is current going down? But you're still using your right hand following current in this rule. So here's some example problems. What direction is the magnetic field above a wire when current flows towards you? So go ahead and answer this question. And then as you go through here, answer the question and then come back and pause it as you need to and then check the answers. Okay, so this one would have been to the left. So it's asking you about above the wire, when the wire is facing towards you. So you're holding your hand towards you and top of your fingers, the curl of your hand would be facing to the left. What direction is the magnetic field to the right of a wire when current flows away from you? So go ahead and take your hand and turn it away from you and then look. Okay, so to the right of the wire, which way would it be going? And that would be this one right here. So current going away from you, that's the eye right here. And then the magnetic, your curl of your hand, your fingers are doing this. When you're holding it away, your thumb would be facing, it's an ugly looking hand, but your thumb would be facing that way into the page or into the screen. What direction is the magnetic field in front of a wire when current is flowing up? So take your thumb, face it upwards, and then take a look in front of the wire, which way is the curl of your hand going? And it would be your curl of your hand would be, your hand would be going from back there, like this. Your thumb would be facing into that little tiny thumb. Your thumb would be facing up, and then this would be to the right. Okay, so we're going to take this, we're going to take it to the next step. Now we still have this current flowing through a wire, but now we're going to have this thing called a solenoid. We're going to still go with the dots here represent a positive flow from positive to negative, not what really happens, but conventional current. So positive flow that Benjamin Franklin kind of came up with, going around, follow it through. And a solenoid is going to be something that's very important. If you ever open up a device that moves a motor, you're going to see a solenoid being, a major part of it. You'll see magnet, this orange-looking wire, usually a red-looking wire in there. But a solenoid is nothing more than a coil of wire. So that's all it is, a coil of conductive wire. So we have to be able to run a current through it. And also, it has to have either some insulation and that insulation could be air. So the way I drew this solenoid right here, where I have this animation going on, this wire is not touching any other part of the wire. If these two parts were closer together and they were touching, current would not want to go around and around and around. Current would want to go straight ahead. So you need some sort of insulation, and that insulation can be air, or often in the stuff that we probably use in class called magnet wire, they'll use an enamel, a polish on top of it. So each time that the wire coils around, notice how on our side, the screen's on your side of the screen, it's going all the current's going to the right, and behind it, current's going to the left. So that's going all the way around. Ignore this part right here when you're thinking about it. You're just looking at this part of the solenoid when you answer any questions here. So what's a solenoid? If you haven't answered it already, answer it now. It's a coiled conductive wire. Using a straight line current right hand rule with a solenoid, observe how the right hand follows the clockwise current in a solenoid. So what you might see is you might have a question where it says, okay, current's going this way. What direction is the magnetic field as a result? Or it might say inside this ring, where current's following that way, with the magnetic field be towards you or away from you. And so if you just grab, just like you see here, you just grab the wire. If you know that the current's going this way around, you would just grab the wire. In this case, you'd want to be above the wire, and you would follow that current, and your hand would be going towards you here. And I'm going to not use that arrow because it looks like up, towards you here, and then the curl of your hand, so you wouldn't see the wire. The wire would be the wire would be underneath it. So if I want to draw it a little bit better, my thumb just disappeared. It could look something like that. I don't know if I call that better, but I drew it. And so on this side, your fingers are facing towards the screen. On this side, the curl of your hand would be you'd be going towards you. So the thumb follows the direction of current. The curl of the hand is in the direction of the magnetic field, and your fingers are facing downwards on the outside of this ring, facing towards you on the inside of this ring. So when we have counterclockwise current, we just went ahead and switched everything around. Well, now we have counterclockwise current. We also switched the way that the field, the magnetic field is going to be pointing. So just picture an area where you would grab the ring. If you grab the ring, you'd want to make sure your thumb's facing that way. Grab your ring so your thumb is facing that way, and then you can look at the curl of your fingers, and the curl of your fingers would be, so you grab it like this. The curl of your fingers are facing inwards on the outside, and it would be the curl of your fingers. If you just rolled your hand around that wire on the inside, it's going to be facing towards you. So when we have clockwise current around a solenoid, so now we're going to go ahead and we're going around this way, clockwise like a clock. We would go ahead and we would grab that solenoid. We're going to go ahead and we'll take our right hand, and we're going to want to put our right hand over here. We can put our right hand over here. We can grab that wire, and our fingers would be wrapping outside like this. So if you use your right hand, your hand would be right there, and on the inside, I guess I didn't do that in a very great way. Let's do this again. And so if I went ahead and grabbed that, I made my thumb go the right direction, your actual fingers are going to be curling from behind it, going in front. And so the magnetic field's coming towards you out here. And then if you just kept on curling around that wire, at some point in time, your fingers, once you got to the inside, are going to be facing inwards. So the magnetic field would be inside in the middle of this. Okay, so we have an electromagnet. You should know what this is. And we're going to take a solenoid, and we're going to go ahead and we're going to put a soft iron core in it. And so instead of what you see right here, where we have this magnetic field produced, well, we're going to go ahead and we're going to take something that's, when we say soft, we mean that these domains inside can align, and they're going to align with this magnetic field. So it's going to be a lot stronger. We have a soft iron core because all the domains are going to be aligned a certain direction, so that one direction is north and one direction is south. But an electromagnet has the solenoid, the wraps of wire, and then a soft iron core that's going to be aligned. This current in the solenoid is going to align this so that one direction is north and one direction is south. And in order to know that, we would need to know which direction current's flowing, or which side's the positive, negative, or we might see this designation that current is flowing this way right here. So what makes up an electromagnet? We're going to have solenoid, the coils of wire, and we're going to have that soft iron core. And then here's your right-hand rule with electromagnet. So what you're going to have to do is take a look at this. I have the positive terminal right there. I'm going to have the negative terminal right there. So therefore, current would rotate, would go underneath. So underneath this electromagnet, roll up top, underneath, up top, and it's going to do that, and it's going to come out this direction right here. So what you want to do is you want to, in this right-hand rule, your thumb will represent the north pole of the magnet. This is going to be the result of the direction of current. So you're actually going to do this first. You're going to find current, and then you're going to look at which way your thumb's facing. So this is actually the second part that you're going to do. So current is, so let's go ahead and get your pencil again, but this time your pencil is the soft iron core, and you want to wrap your fingers around it so that your hand, the back of your palm should be underneath the solenoid with the soft iron core, and your fingers should be revolving around to the front. And the reason why this is the case is because current is going from behind it. So the curl of your hand should be behind it around the front, just like you see here. And now look at the direction your thumb is. The direction of your thumb is the resulting direction from following the current and curling your hand around the way that the current would travel around the electromagnet tells you where the north is going to be, or tells you where the south is going to be, because you can have dipoles, so a north and a south are going to be created at the same time. So if one side's north, the other side has to be south. So here you go, wrap your hand around the direction that you see the current, and then look at your thumb as a result. And we're going to try a couple of these practice problems in a second. Okay, so if we go ahead and notice the difference here. This time we have current going, the positive terminal, the direction where current's starting is going over top and wrapping around. So take your hand, and once again, your pencil can be the soft iron core with the solenoid around it. Well, you want to make sure you can see the back of your hand because current's flowing over top of this thing. And now look at the result. Look at the direction your thumb is facing. That's going to be the direction that the north of a compass would be. And therefore, if you had a magnet next to it, the north is going to attract to south. So the magnet will be facing in this, or the compass would be facing, a freely rotating magnet would be facing with south towards your thumb, and then the north in the same direction as your thumb. Okay, and then there's ways to strengthen electromagnet. You need to know these. First of all, if we have way more coils in the solenoid, so I could have the same battery power and therefore current that results from this voltage, but this would create a stronger magnet by just having more coils around. I would be able to pick up more paper clips if I was trying to pick up paper clips. It's in the lab I'll have you do if we can do it this year. Or I can go ahead and I can have the same amount of coils, so increase the number of coils in the solenoid like you see right here, or I can increase the current. So I can have the same number of coils, spacing is the same, there's still 1, 2, 3, 4, 5, 6, but plug it into a 12-volt battery and you're going to be pumping a bigger current through there, and therefore this would be a stronger electromagnet as well. So here's your question: what are 2 ways to strengthen an electromagnet? So the first way is we're going to increase the number of coils in the solenoid. Second one, we're going to increase the current. If you can do both of these, we'd have the strongest electromagnet on top of having a soft iron core. The solenoid itself with pumping electricity, pumping a current through there, is magnetic on its own, but you need a soft iron core to really make it stronger. Here's your question: which combination would lead to the greatest increase in the strength of electromagnet? Let's go ahead and take this second and answer this question. That's going to be increasing the voltage and increasing the number of coils. So therefore, you're increasing the current because of that. You're increasing the number of coils of the solenoid because of that. So your answer is going to be C. So next question: what would happen to an electromagnet if you switch the direction of current of the solenoid around it? And so the north and south poles would flip as a result. You'd have your hand facing the other direction, and therefore your thumb would be facing the other direction. Okay, in this question, what pole would be at the bottom of the electromagnet when currents run in the direction seen here? So grab that pencil, and here the positive terminal would be there, negative terminal would be there. Have your hand so it's wrapping around this way, and then take a look at the direction your thumb is facing. And so your thumb, if you held this, your hand would be over top, and your thumb would be facing upwards because your hand would be over top, so you wouldn't see all this. And then therefore the south would have been the other side. What pole, no, not what pole, let me fix that. What pole of the electromagnet would be on the right below the battery if a battery was attached this way? So therefore current is going to be facing, you want your curl of your hand to go over top. You want to make sure if you're looking at your hand, you're going to go ahead and look at it so you're curling over top of it. So my fingers going that way, and then you take a look at the direction your thumb is facing, and that would be north. North of the compass would be right there. Okay, now if we grabbed a loop, what direction would the current flow? So, okay, so I would need to grab a loop in a way that my fingers would be coming up from the inside. So there's your fingers. Let's see. So I grab that loop, holding your pencil, like just pretend, just ignore all the rest of this and just pretend like the pencil's right there. And you want your fingers coming at towards you. So you want your fingers coming from this side towards you, your hands back here. And so therefore, it says what direction would the current flow? And it's going to flow just like you see it. I'm just holding the way I drew this, I'm holding the tube a different way, but if you notice the thumb's still facing the same direction. So no matter if it's the same right hand, it just depends on if I'm in front or behind it, but I'm following the direction of my finger, and then that would be counterclockwise. What direction would the magnetic field be pointing towards if you have this going on? Is it going to be facing towards you or away from you? So you want to go ahead and you want to pretend like you're grabbing. Once again, just look at this part, pretend like that is the part of a wire, and you want to grab it so that your thumb is facing this direction. And we grab it so your thumb is facing that direction. And it's kind of hard to draw this so it looks the way it should look. But if you do it right, you can have your hand, your thumb's going to be facing that direction. I can't really draw it well, but if you can kind of get the contour, you're going to see that it's going to be towards the screen inwards on the inside.